Okay, so I think it's now 11:05. Welcome everyone to today's live session. It's a pleasure to meet all of you weekly to have discussion on the activities that is actually ongoing on DE Africa and also some of the products and notebooks that you can actually use DE Africa to develop. Today within our midst, we have Chad from Geoscience Australia who will actually be uh, presenting for us today. So at this point, I will hand it over to Chad.
Okay, thank you, Edward. I'll turn my screen off in a second in case any of you are having bandwidth problems, but I just thought while I introduce myself, I'll leave it on. So yeah, as I was saying, I work for Geoscience Australia, and I've been working with the Digital Earth Africa program, not quite since its inception, but from the early days. Certainly from the early days when the sandbox first became a thing that you're all using now. So. And I'm kind of leading this, I'm sort of co-leading the science effort on Digital Earth Africa's side. And I was the principal investigator for the crop mask that some of you might have seen. So today, in the spirit of leading that crop mask effort, I thought that I could focus on that today. I haven't been to one of these live sessions before, so please tell me if I'm going a little bit too off topic or it's not, or there's some area that you want me to specifically focus on. Just let me know, and happy to please take questions. Let's keep it informal. Just ask questions as I go, or whatever, or if you want clarifications. So what I've got today is I've got 5 slides I'm going to show you, and then I'm going to go through a series of notebooks. So let me jump into it. All right, I'll turn my video off and I'll start sharing my screen. Just let me know when you can see that.
Yes, we can see
Yep.
it.
All good. Yep. Okay, cool. So the Digital Earth Africa's cropland extent product. It will be a continental product eventually when I get there, but at the moment it's 3 crop masks, crop mask, cropland extent. I kind of use those terms interchangeably, but at the moment it covers East Africa, North Africa, and West Africa. They're the ones that you can currently load in the sandbox, and the names of all of them that you load in the sandbox are there highlighted in bold. So if you're doing your datacube.load, then these are the names that you use to load them. And these crop masks cover the countries that are listed there. And just a screenshot there on the right. So the cropland extent product, it's at 10 meters resolution. It has 3 bands related to it. It has a mask band, which is the one you see here. It has a band called filtered, which is an object-based crop mask. So some of these pixel-based results have been cleaned up a little bit. And then there's a probability layer, which I'll show you in a minute. So
hi, Chad.
Yeah.
I'm sorry. Are you able to go into presentation mode so we can see the text a bit?
Oh, okay. Yeah. Hold on. Sure. Is that better? Can you see that?
Yeah, Chad, it's better. It's better now. Yeah.
Cool,
Thank you.
Yeah. So I've got a very big screen here. It's quite easy for me to see. So yeah, the cropland extent map has 10 meter resolution. It has 3 bands with it, and at the moment it just exists for 2019. So it was made using Sentinel-2 data from 2019, and in the future we'll probably produce it for future years. But at the moment we're just concentrating on building the continental crop mask for 2019. So like I said, there's these 3 products that currently exist. If you're interested in their accuracy, using that validation data set there that you can see on the left, we've got roughly 1,800 samples across the continent that form our validation samples. And the crop masks were produced with the training data that you see on the right. So the East Africa crop mask has an overall accuracy of about 90% and an F-score of 0.85. And if you're not familiar with the F-score, it's just a bit more of a balanced way to understand accuracy. So overall accuracy is okay as a measure, but if, for example, you have a lot of non-crop points and very few crop points, you can make your overall accuracy look better if you have an unbalanced data set there. So the F scores are sort of harsher but more realistic estimate of the accuracy. The West Africa crop mask is about 83, nearly 84% accurate, an F score of 75. And the North Africa crop mask has a 94% accuracy and a F score of 0.91. How these compare, these values, is this any good? These are sort of global, so these are statistics, averaged across the whole crop mask, so in some places, the crop mask is really, really good. In other places, you'll find errors, but the models were built to sort of balance those errors. So I tried to focus on having balanced errors. So you'll see the ratio of emissions to commissions is not too bad. So depending on where you are, you can assess that accuracy for yourself. But how they compare to other products that are the products that are out there, I will show you how they compare to the land use land cover products that we have indexed in Digital North Africa soon. But there's not a lot of products that are this sort of high resolution across the continent to compare to, but overall accuracy compares quite favorably for this product. So this is as good as or better than any of the products that currently exist for Africa. And then I wanted to put a slide here to say that there are more masks coming soon. So I see Bako's on the call there. So the crop mask for Sahel will be coming out in the next month, as well as this one for the southern area. And then the southeast, which covers Zambia, Mozambique, etc. I hope to have that one by the end of the year, but maybe it might be early next year. So the rest of the continent will come along quickly. And I got some resources and links here. So I'm going to go through all of these. So that we're going to go through the dataset specifications notebook, which if you use this, you can use this one to understand all of the, how would you say, all the technical details of the product. How the algorithm was made. You can, inside the dataset specifications notebook, you can click on links to get the training data if you want to download the training data yourself. Instead of just having just overall accuracy reported there are actually confusion matrices, so you can see exactly how the validation statistics work. And then we have this datasets notebook here, and that's the sandbox notebook that shows you how to load the crop mask and some of the features of it, and then it shows a few of the, like a couple of basic examples. And then there's these more elaborate examples, if you like, the crop phenology, which is some screenshots here along the bottom for a region. I've got optical and radar versions of those that make use of the crop mask. And we've got an NDVI Anomalies notebook that also uses the crop mask. So you can use that to map crop anomalies. And the last one, I'm not going to go through in detail, but I will show it to you where you can say for if you've got a small region and the crop mask is not very good in that region, you can look about creating your own crop mask using this machine learning workflow, which I think some of our partners are working on particular versions for at a country scale or less. So if I think that's the last slide I had there. Yeah, so I'll just get out of presentation mode if I can figure out how. There we go. So are there any questions there before I move on and start showing some of these notebooks in the sandbox?
Hi, Chad. Yes, I have a very brief question to ask.
Yeah,
so
please.
When you talk about crop mask, what kind of crops are you looking at? Are we looking at both annuals and perennials?
Yeah,
or...
Yep, sure. So in the dataset it's a great question. In the dataset specifications notebook, which is this first one here that I linked. So maybe you've seen these pages before. We have these sort of very long technical explanations for the products, for each of our products. And this is the cropland extent one. And here I have the definition I use for cropping. So there it is. So essentially a pixel, a 10 by 10 meter pixel that's sowed or planted and harvestable at least once within the 12 months after the sowing and planting date. So perennials will be excluded as well as grazing lands. That's because it's just very difficult. Perennial tree, citrus trees are very hard to distinguish from other kinds of forest, right? So you're better off just excluding that from your definition. I will say about this 12 months, the training, when we collected our training data, there were exceptions to that. So I think maize has a longer than 12-month planting cycle, but we still included maize in our training data. So we should be mapping maize. So this 12 months isn't very strict, but yeah, I understand the definition as really anything that's being planted and sowed in a reasonable amount of time.
So if I understood you clearly, you are saying that the mask is based on pretty much annuals, right?
Yes.
And not perennial.
Yes.
Okay.
Not perennials. That's right. Yeah.
Okay. All right. Thank you.
Yeah. Which is a very this is a very common definition for cropland from a remote sensing point of view. Yeah.
That's right.
Yeah. But with that said, remember that this is a machine learning workflow, and obviously we collect training data. When we're collecting training data, it wasn't just me that collected. Of course, it was a lot of people, but we kept this definition in mind the whole time. However, what happens inside the machine learning model is a black box. And so sometimes, of course, perennial crops are mapped as crops for whatever reason. I can't tell you why. There's no training data that says it, but for whatever reason, it maps it as a crop. So yeah, you try to maintain this, but you don't know what the model is going to actually spit out at the end. All you do is look to get the most accurate model you can. All right. So any other questions there? Okay. So I'm going to just move through some of these.
I have a question. I didn't, maybe I missed it. The difference between optical and radar when you presented it, which one is?
Oh, this one here. This is an optical one. Yep, and I can show you the radar one as well if you like in a moment. Well, I mean, I just click on it. Let's wait for it to load. So some of you, I'm not sure, like, I believe at previous live sessions we've presented on Phenology notebooks, but I recently updated all of these and included a radar one. So they should be a lot better than they used to be. So this is the radar one using Sentinel-1 for the same area. So yeah, you can see the radar index there. Smooth it out to get the time series. And then we try to, oh, there you go. We try to plot the start and beginning ends of the seasons. And we've got a plot at the end. It's a bit noisier than the optical one. But of course, if you're in a very cloudy area, you can't even use the optical one. So this gives you an alternative. Yeah. So the datasets notebooks, I'm just going to, just to reiterate, I'm going to just move through these. So these kind of go from like less complicated to more complicated in terms of the examples. But this is the specifications notebook. Just to give you an idea of a few of the different headings here, we've got the definition, got some accuracy stuff here, tells you a bit about what the measurements are in the cropland product. I should probably, so why don't I pause here and I'll show you the map to understand that. So we've got the mask, the probability, and the filtered layer. So the mask is literally just the pixels. Let's just zoom in. So you see the mask is this cropland one, right? And it's just pixel based stuff. So every single, you can get like an individual pixel is labeled as crop, you see? And then we can go, so that the second one here, oops, sorry. This one here is, just consider the filtered one. So this is an object-based filtering. So if we do this one, you'll see you don't get any more single pixels. So it kind of cleans it up a bit compared to, again, the pixels. So in some cases, this really this can improve the crop mask. In other places, it might remove legitimately small cropping fields. So you kind of we provide both of them rather than saying, oh, I could have just provided the object-based one, but we want to provide both of them so that the user, so that you guys can decide what's the best one for your situation. And then we have the probability of cropping. So this is, so if you just click on any one of these, you see the probability here is 88%. And what that means is that 88%, because this is a random forest model, a random forest machine learning model, and that means that 88% of the trees in that random forest, of the decision trees, voted for that class as crop. So you can consider that a kind of rough approximation of how confident the model is that it's crop. Whereas, over here, where it's not crop, we have a very low 10%. So effectively, if you thresholded this product, if you thresholded this band at 50%, you would end up with this. Does that make sense? I hope so. A few more. So the going back through the dataset specifications notebook, you can see that it's 10-meter resolution. It comes in the equal area projection. It was built from using the Sentinel-2 semi-annual geomads. What else is interesting here? So there's the algorithm that shows you how it was built. So you can see there's a random forest classifier with a bunch of band indices and the geomedians going in there. If you want to access the training data yourself, you can. It's here. So say for the East Africa, you can see there's all the points. Well, actually, they're tiny little polygons. So there's all these little polygons here. So you can go get that training data if you want, and then the validation samples are they're as shape files. So you just go to our crop mask repository, go down here, validation samples, and you can download them. And then I've got a lot of information on how we did the validation. You've seen that one before, and then you can see that we have these confusion matrices for each of the different crop masks, which give you the detail of how they achieve that overall accuracy assessment. Okay. So moving on from the dataset specifications notebook, I wanted to show you how to load the data in the data cube. So in the sandbox, I'll assume you're all familiar with the sandbox. So we just go here into this datasets folder, and it's the cropland extent one. I've got a bit more information here about what all the products are called. And then I've also got links to some of the use case examples. So if I just run through this one and show you, so we've got so we're going to just load it for a region. Let's have a look where it is. Pretty sure this is Ethiopia. Yep. There you can see where we are. We can list all the different products. So like I said, crop mask, northern, eastern, western, and then these are the three bands that I was just describing: the mask, the probability, and the filtered. To load it is super easy. You just pass your normal queries, your lat range, your time range. The time range is always 2019 at the moment, so don't worry about that. And your resolution. So the native resolution is 10 meters, but if you wanted to, you could load it at a higher at a coarser resolution if you wanted to load a really big area or something. Simple as that. We can see there's always this one time step, and we've got our 3 layers. We can plot all of those. So again, it's just an example of the pixel based versus the filtered, and then the probability. So you can see here, if you thresholded this at 50%, you would get this at this same area. And a really simple example of using it, I can load some Sentinel-2 data for the year of 2019. Calculate NDVI. Apologies if this is a little bit slow. Because we're loading such a long time series here, I do some resampling just to make it a monthly. So we just get one value per month, and that'll help smooth out the time series. I don't know how much of you have used Sentinel-2, but the cloud mask is not very good. So sometimes doing things like resampling to a mean can just remove some of that noise. We can now we can use our cropland extent to mask that region. So we're just looking at the cropland. You can already see your results. And then we can see the phenology for the cropland in that area, which we can see gets planted sometime in the early to middle of the year, and then isn't actually probably gets harvested in the early new year. So the second example that I've included on this notebook is in a comparison with the global land cover data sets. So this is another recent addition we have in our data sets is these land cover data sets. So we've got one from ESRI or Impact Observatory and another from ESA. These are 10-meter resolution land use land cover maps with these fields. So for example, you can load that in that's their crop class. I think this is from 2020, their map. So, broad, in this case, it's showing broadly the same areas. So we do a comparison here. I've done a comparison here for, in Uganda. So there's this big cropping region here around the lake, and it's extensively cropped. If anyone else is familiar with the region, and I load our crop mask over that region, and I load the ESRI and ESA land use land cover data sets, but I'm just grabbing the crop class. So I'm just grabbing their crop class with these statements. And then we can plot the extent of them. So you can see they differ wildly, right? Digital Earth Africa's, ESRI, and ESA. So you can see that they vary a lot, and how well they do really depends on where you're looking. So, and then it's very easy to do the difference in area between those, and you can see that it makes a huge difference, obviously. So in this particular example, Digital Earth Africa's crop mask is much better. This really is all cropping, except in here, there's wetland over here. There's wetlands intermingled with the cropping. So this is where we get a few commission errors. So none of these get commission errors here, but of course they have a lot of emission errors. They're missing a lot of cropping. So on the whole, it's fair to say that Digital Earth Africa's cropland extent map is, for the crop class, is much more accurate than any of the land use of the global land use land cover maps that currently exist at that 10-meter resolution. Okay, any questions there on that one? Am I going too slow or too fast? Ken, Edward?
Hello, Chad. I think hello, Majari, please, you can go.
Thank you. Thank you. I have a question in the final output.
Mm-hmm.
I think for the different, no, not this one, the one with many, not this one, the like six, I don't know if it is in this or in your previous presentation, like it was explaining the different stages, the different
phenology.
Yes.
Okay. All right. Let's just get to that example now. So
okay.
that was here. Yeah. So that was I wanted to show you. So we looked at the dataset specifications notebook where all the technical information is.
Oh,
so
okay.
So right, that one I just showed you. This one here. This is the datasets notebook, which shows you how to load the crop mask, and then it has a couple of simple examples, straightforward examples. So, so yeah, this is the cropland extent maps for Africa, and then now we'll go into some more complicated use cases. So this one here is the crop phenology. So let's.
Oh, I confused the two graphs. Thank you.
That's all good. That's all good. Yeah. So let's have a look at that one now. Frequently used code. Oh, sorry. Apologies. It's in real world examples, and where are we? Phenology optical. Here we go. So vegetation phenology, we're going to use Sentinel-2. So let's just run all these cells and then we'll move through them. So this one, where I'll probably use the same example, do I? Let's see if I hopefully, maybe I did a different region. That would be interesting. No, sorry, I use the same region. Anyway, so we're going to look at that same area. It's going to load data for, let's have a look. Is it all of 2019? Ah, okay, it's loading data for 2 years from 2019 to 2020. Load the crop mask over the same area. NDVI. Hopefully that's all familiar to you. So it's important when you're, so yeah, here we go. So that gives you an idea of the crop mask. This is I've just plotted a couple of examples, right? So you can see it's started off, yeah, it's good. See that it's graining up and then we're missing time series as well. So yeah, I try to show you this example, how noisy the time series can be. So for example, this here is cloud that we've missed, that the cloud mask has missed. And you can see there's quite a bit of noise, right? From measurement to measurement. So it's important that if you're using these phenology notebooks, that you pay the right amount of attention to smoothing and interpolating that vegetation time series, so that you. What I'm trying to say is that the results that come out at the end are directly related to how well you can make, how nice you can make this curve. So if you just chucked this time series in, you'll get terrible results in the phenology. So it's important to step through these examples. So here you can see I've smoothed it out a lot. So we clean up the time series, and then we're going to calculate these statistics. So I don't know how familiar people are with phenology, but this is the start of the year. So they're recorded in days since the start of the year, where January 1st is 1 and December the 31st is 365. So that's start of the year, start of the season, I should say, start of the cropping season. The value at the start of the season, so the NDVI at the start of the season, the peak of the season, what day the peak of the season happens, and the NDVI at the peak of the season. And then we have end of the season, NDVI at the end of the season, trough, meaning what was the lowest point in the time series, the length of the season, so that'll be in days, the amplitude of the season, which will be the difference between the trough and the peak in NDVI values, and the rate of growth and the rate of senescence. And there are different methods for measuring, for deciding how you measure phenology, essentially. So you can read, I won't go into it, but you can read these details here. And you can see, so for year 2019, the start of the season was day 90, and in 2020, it was later, according to this time series at least. Remember, this is averaged across that whole area, right? This is not one pixel, this is all those pixels. We can see that the value at the start of the season for NDVI was 0.198. The peak of the season was right at the end of the year, and the value, the NDVI at the end of the year was quite high. You can see compared to 6.1, we had 6 here. Yeah, and then this is summarizing that whole area, like as a single time series. And then the next ones are per pixel phenology statistics. So that'll show it for the cropping area. You'll have the start of the season from 1 to 365, the NDVI at the start of the season, etc. Another thing that people often do is they won't do it like, they won't have one for 2019 and one for 2020. They'll take the average of both of these. So they'll group by year, and then they'll take a mean, say, or a median or something for the year. So you might load 3 or 4 years, take the mean, and then produce one of these. So you have a kind of average phenology for that region, as opposed to looking how the phenology changes year to year. So yeah, so that it gives these nice outputs at the end. So you can see those. One thing I'll say, of course, is that phenology is a little bit tricky. So sometimes if this, say that this year was, say that the year, the peak kind of crossed the end of the year, then that could mess up these statistics at the end. If this peak happens right at the end of the year, then it's very difficult for it to try and estimate the end of the year. So it kind of messes with it. So you just got to you got to take it on a case by case basis, is what I'm trying to say. All right. And then the phenology radar is exactly the same as just using the Sentinel-1 instead of Sentinel-2. Yep, same time period. It's the same region. So just this time though, we're loading Sentinel-1, loading it at 20-meter resolution. Got our crop mask. This is the time series. So you can see this is not, this is a false color image using backscatter, but you can see it's changing throughout the year. We have this thing called the radar vegetation index, which is calculated like this. So there we go, we produce it. Again, it's a bit noisy because of the different, in this case, it's not noisy because of mist cloud in the cloud mask, but it's noisy because of the different view angles of the satellite. Again, it's obvious. Sorry.
I have a question with the noisy part. Like, how would you know if it's noisy or not? Will it mean like there's a drastic change in the peak, or how would you determine?
Well, I mean, just you wouldn't expect a cropping region when you're averaging it across this whole area to have these jumps like this, right? Like what if we were thinking that this was purely, okay, so some of this would be, I guess it's experience mostly. So, and understanding something about the satellite. So some of this might be like, say, if they were watering, if there was rainfall event and the crops are very wet or the soil was very wet, that might change the radar signal. But I also know that the data set we've loaded here, Sentinel-1, it has 2 different orbit directions. It orbits like down and up. And so when you're looking at those different angles, you get a slightly different value, and that creates a bit of this sort of jitter, if you like, this sort of up and down like this. So that's why when you take an average of those things, like you take a rolling median, then you kind of smooth that out. But yeah, it's partly just looking for things that are like in this one here. This is really unlikely to be anything physical, right? Anything to do with what's happening on the ground. All this here as well, right? This is clearly just NDVI is being messed up by mist cloud in the cloud mask. So cloud is creeping into our clean data set and producing funky NDVI values. So again, that's just kind of experience with this data set. I know that these kinds of things are going to happen.
All right, Chad.
Yeah.
So I have a quick follow-up question. How does the platform handle these cloud issues in terms of cloud masking and all that?
Like, how do we make cloud masks, or how do we handle them not being
that great? So for this kind of things you are seeing with these spikes you see, definitely you are attributing that to clouds, isn't it?
Yeah.
So I'm asking how you treat this if you want to get a smoother curve, how you treat the cloud cover issues.
Okay. There are a few different ways. There's a couple of different ways to do it. So when have you used load ARD before? This function?
Again?
Have you used this function load ARD to load data from the sandbox?
No.
Okay, so this is our wrapper function that we use. Okay. And what it does is basically you say, I want to load Sentinel-2, and it loads it and it cloud masks it itself. Okay, so under the hood, it does the cloud masking for you. So it applies the pixel quality cloud mask. But of course,
so it does some cloud masking, right?
Yes, all of this is cloud. This data set has been cloud masked. There's no cloud in this, right? The problem is just that the cloud masks aren't always that accurate, especially for Sentinel-2.
Okay.
And that's a problem with the satellite itself. It doesn't have a thermal band, which means that it can't detect cold cloud tops. So it has to use different approaches. And so, even if it's like 95% accurate, that 5% is really annoying, you know. So I won't go into details with it here, but one way you can do it is providing this mask filters option. Now these are morphological filters that operate on binary masks, binary cloud, not cloud masks, and they try to improve it by dilating the mask. So sometimes you just make the mask a little bit bigger, and that will capture some of that mist cloud or mist cloud shadow. And then this opening one, what that does is what we often find is that, like, if you're working on a coastline, it'll accidentally, the bright beach sand will get classified as cloud. And so you can use these opening operators, which will remove those weird long strips of cloud, which probably aren't cloud, but are actually like maybe something in a city or they're a beach. So we do these. So this can improve the cloud mask a little bit.
Okay.
However, it doesn't get rid of everything. The other thing you can do, is you can filter by unusually high values. So usually the blue band is helpful. I don't know if I loaded the blue. Oh yeah, I do. So maybe I can do like a dot blue, right? And we can go where it's less than, let's say where it's greater than, say, 4,000. Yeah, so you can do something like, so the values go from 0 to 10,000. And if you have a really high blue value, that probably means it's mist cloud. So you can filter your data set by anywhere where the blue band happens to be very high, and you'll be pretty confident that that's probably cloud. So that's a kind of crude way that you can do, but you have to sort of test it and see that that's going on. Yeah.
All right.
Yeah, and then that might get rid of these peaks. Or you can do what I did here and just heavily filter and resample the data set. So we resample it to every 2 weeks, and then I do a rolling median, a rolling mean, sorry, over as well to smooth it out. So that sort of took these 2 big peaks and turned them into these little blips, you know. So that's the other way to do it. Yeah.
Yeah, that looks interesting.
Yeah. So yeah, we call it analysis ready, and it is, but obviously all these data sets have limitations, and then just your experience with them, you'll figure out where they work best and where they don't, and what you need to do to improve them. So yeah.
Right.
Yep. And so yeah, sorry, I don't know where I got with this one, but basically, yeah, it's exactly the same as the other one. It's just using radar, and the values will differ a little bit, but the general trend will be the same. So yeah. All right. So that's those 2 examples. I should hurry along a little bit, shouldn't I? Okay. And we've got the NDVI Anomalies one. So let's say, spoiler, a bit of a spoiler that we have this notebook that'll do NDVI Anomalies, but Edward and I are working on building an actual product that you can just load that does NDVI Anomalies. So in the future, you won't have to use this notebook. You can just load them. We're doing them over the continent at the moment. So this notebook here is going to use the crop mask to mask some Landsat data. And then we're going to calculate the standardized NDVI anomaly for the month, for whatever month that we nominate. So in this case, let's have a look. So we're going to, I won't actually run this because it'll take a little while to run, but you set a baseline period. So this could be, 1985 to 2019. And that will determine the mean NDVI. So let's say July. Let's say we let me start again. Let's say we care about July. We want to know, has the month that's just passed, say it's August, and we're interested, did the month just pass? What was the NDVI anomaly for that month over some cropping region that I care about? Well, we can define a baseline for NDVI from 1985 to now. And we can say, what was the mean NDVI? And what was the standard deviation NDVI around that mean for all the Julys that the Landsat has ever seen for that region? And that's what this notebook does. And then it loads the July for the actual year for 2021, and it compares it to that very long-term mean. And this is for an example in Ethiopia. Again, around Lake Tana, isn't it? Yeah. So this is the pixel count. So what this is saying is that we've got, in some of these places, we have 40 observations of all the Julys in the time series. So from 1985, so in this case, it's from the example that's loaded here is 1999 to 2019. So over that 20-year period, some of these places we saw that we saw that bit of land in July sort of 30 to 35 times. Sometimes we saw it a lot less than that. So we calculate our NDVI climatologies, just like you'd have a rainfall climatology or a temperature climatology. This is essentially NDVI climatology. So it calculates these, and then it calculates the where are we? Yeah, so it's going to calculate the mean, the standard deviation, and then it's going to calculate the anomaly in comparison to that long-term mean of standard deviation for this cropping extent. So that's all masked there. So here we go. This is the main plot, main result. So this is the average July NDVI for those 20 years. This is the standard deviation we see for those regions on NDVI. So it's how variable are these pixels around this mean NDVI. This is what the value actually was in July 2021 NDVI, and this is the deviation measured in standard deviations away from that mean. So you can see that in some places here it's sort of 1 to 1.5, maybe some places approaching 2 standard deviations away from the long-term mean, which means it's a fairly negative event. Maybe crop failures, or maybe people aren't cropping this year, I'm not sure. So that's something you can do for really any region in Africa. And we also have a seasonal version, monthly and seasonal. Okay, and I'll just jump very quickly into this last bit and then have questions. I don't know if it's been covered in a previous live session or not, but we have this folder here called Scalable Machine Learning. And it steps you through is this 5-step procedure in starting with some training data and ending up with a classification. And essentially what this does is it produces a crop mask. It's not exactly the workflow that I use to make the crop masks that you can load now, but it's very close. And so if you have your own training data, or if you want to grab some of that training data that I've got linked here that you could grab, you could take a subsample of that for a particular area you care about, grab your own training data if you want, and if you ran through these notebooks, you could come up with your own crop mask classification. So classified image, this is the geomedian and the probabilities. So you can do all of these. So I just wanted to highlight there. I'm not going to go into any detail, but yeah, if you're interested more in the crop mask and how it's made, then this might be an interesting place to work through. I think that's all I want to cover off on today. I know that was a lot and I went through it fairly quickly, but hopefully that gives you an idea of how the crop mask is made, how you can load it, and how you can use it. That's my hope here today, and how you can make your own. Thank you.